Okay, good. I guess evening, morning, whenever you're looking at this, watching this. And hey, I wanted to give you just a heads up. I am recording this at home because it's Sunday when I'm doing this, and I really don't feel like going to my office. So, uh, so if you hear background noise like motorcycles and cars going up and down the street in front of me, I apologize. Hopefully, it won't be that bad. Okay, so the next 2 weeks we're going to be talking about the happy brain. So, and here's how we're going to go with this. We're going to start with a little bit of time talking about dopamine. The paper that you have to read for Tuesday is sort of an overview of dopamine and how we thought it was the pleasure neurotransmitter and how not quite as simple as that. So we're going to talk a little bit about dopamine. This is my opportunity to review this because it is a really important neurotransmitter when it comes to behavior, cognition, and all the things that are near and dear to our heart. We're going to look at dopamine in terms of both motivational characteristics. This what you'll learn is called wanting, compared to hedonics, or the affective component of behavior. And we'll be referring to that as liking, and how these two are separate and are being driven by separate neural systems. We'll also have a little bit of a shout out to learning, because learning does play a role in some of this. But again, it's not as simple as we had once thought. And then we're going to add in the mix some endogenous opioids or endorphins and the endogenous cannabinoids, or your brain's own marijuana, and how these two are very important for this part, that is the hedonic part or the liking part. I'm going to try to relate some of this to the control feeding. So we can spend a little bit of time talking about how hedonics or pleasure, the affective component of behavior, can help explain why we eat what we eat. We talk about things like cue potentiated eating, so you eat more when certain cues are presented to you. A concept known as alliesthesia, which I will spell out later, which essentially says that the more useful something is to you, the more you like it. So we'll talk about hunger and how hunger makes food taste better. And then finally, we're going to talk about a human study that looked at opioids, endogenous opioids, and their release when you're hungry. This will all be this week, and then next week we're going to move over to talking about play, the pleasures of play. We'll start with just some of the neurotransmitters that are involved in play, maybe some of the brain systems, trying to compare it to what we know about reward associated with other kinds of behaviors. We're going to focus on motivation to play compared to the reward associated with play, sort of paralleling with what's going on up here. And then finally, on the last day, the following Thursday, we will talk about laughing rats. You'll learn about ultrasonic vocalizations. We're going to talk about tickling some rats, and then finally wrap it up with rats playing hide and seek. Okay? Cool. Okay, so let's start with dopamine. This is going to be a bit of a review, but like I said, dopamine is a pretty important neurotransmitter, so it is kind of worth going over it and making sure that when you leave a course like this, you have a fairly good grasp of what dopamine does. Here's the rat brain. Dopamine's up there. Here's the actual molecule of dopamine. It's funny, I once had a student who worked in my lab for a number of years, probably from a sophomore till she graduated, and her sister came along about a year or two later. She took this course, really decided she didn't like brain and behavior, didn't like psychology. She did well in the course, ended up being majoring in OMS, and she came to my office one day and says, "Hey, I got to show you what I did." And she had tattooed dopamine, this dopamine molecule, on her ankle. It's like, seriously? I would have expected that from her sister. But in any event, so if any of you are looking for an interesting tattoo, here you go. Okay, so this is the dopamine neuropathic pathway. The two we're going to talk about, we'll talk initially about this one, the substantia nigra, sending up to the caudate nucleus, sending up to the basal ganglia. But then we'll focus more on the ventral tegmental area, and primarily its projection up here into the nucleus accumbens. But notice it also sends input to the amygdala as well as up here into the cortex. In terms of the synapse, dopamine synapse, we've been through this already. You have dopa becomes dopamine. It is packaged in the synaptic vesicles where it can be released. It can bind to both D1 and D2 receptors. So all the dopamine receptors, we have two major families. D1, the D1 family, and as we're going to see, these tend to be excitatory when they're stimulated. There are two varieties of those receptors. They're called D1 and D5. And then we have the D2 family, which are primarily inhibitory when dopamine binds to a D2 receptor, the net result is inhibition. And there are three subtypes of those receptors, D2, D3, D4. And just in case you're curious, the D5 receptor, why is it up here? Well, I think when they first did this, they laid it out, and it looked like whoever came up with these numbers decided that the D5 receptor was very much like these. And then when the molecular biologists got a hold of this stuff, they said, no, hold on. If you look at this, this is really part of the D1 family, and rather than really muck things up and change everybody's ideas about this, the numbers, they just kept it at D5. Okay, one other thing. Oh yeah, two things. First of all, in this particular scenario, you would not see this. You would not have D1 and D2 receptors at the same postsynaptic neuron, postsynaptic site, because what that would do is cancel each other out. So the D1 receptors are expressed in particular neurons or particular parts of neurons, and the D2 receptors are expressed in different locations or on different neurons. Okay. The other thing is the D2 receptor is also part of is an autoreceptor, so this is the one, when it's stimulated, it'll inhibit further release of the neurotransmitter. Whoa, sorry. Okay, so there we go. Reviewing the major dopamine pathways, the nigrostriatal pathway, substantia nigra up here to the striatum or the basal ganglia, and then we have the mesolimbic and the mesocortical. We can think of these as separate, and it's not a big deal. I think some have traced some of these and find that these are separate neurons. But then even when we talk about mesolimbic dopamine pathway, we're referring to the ventral tegmental area projecting to the nucleus accumbens. When we mention the mesocortical dopamine pathway, we're referring to cells originating in the ventral tegmental area like these, but they are projecting up to the prefrontal cortex. So that would be these, the mesocortical compared to the mesolimbic. And the last bit of review is this terminology that we went over last time. So again, this is a review. We think of the striatum as having a dorsal component and a ventral component. The dorsal component can be made up of the caudate and putamen and the globus pallidus. We refer to these collectively as the basal ganglia. Caudate and putamen would be the input to the basal ganglia, and the globus pallidus primarily the output. In the ventral striatum, we have homologous structures. We have the nucleus accumbens, which is receiving input from the ventral tegmental area. And then we also have the ventral pallidum, which we talked about with the prairie voles, and we're going to come back to this again when we go over hedonics and what Kent Barrett refers to as hedonic hotspots. So input, primarily output, and this would be the mesolimbic dopamine circuitry. Okay, perfect. So we're going to come back. The next one, we're going to go over the role of dopamine in sensory motor functioning.